Hello, everyone. My name is Emma, and I hope I'm a current PhD candidate at there, and I hope to share with you an overview of my current research, which is on structured learning and inference for hybrid Bayesian networks. So Bayesian networks are probabilistic graphical models. They combine graph and probability theory to give a multivariate statistical framework that can support really important components like representation, inference, as well as application to a broad range of problems. A Bayesian network, by definition, consists of a graph structure that is represented by a directed acyclic graph and an associated set of parameters, where each node in the graph is represents a single random variable, and a directed edge indicates probabilistic dependency between the linked nodes. One important feature of DAG is that it's conditionally independent of the sets of all of its predecessors, so that the joint probability distribution can be represented by a product of the conditional distributions given the parents in the graph. So what you're seeing here is an example application of Bayesian networks in gene regulatory structure for dorsal and ventral telecephalon development, which aims to investigate the molecular pathway regulated by proneurogenes to help guide hypothesis testing and hypothesis generation. To highlight key regulators, nodes that are predicted to be parents of at least 9 other genes are the biggest in size, whereas nodes that are predicted to regulate at least 5 other genes are moderate in size. So structured learning for graphical models is still an open area of research. As you can see here, the number of possible graphs as a function of the number of nodes n is super exponential in the number of nodes. So traditionally, we usually have to do a combinatorial search over a very large space of possible structure. And on top of this computational challenge, when working with datasets that contains a mixture of continuous and discrete variables, this is also a big problem. And literature so far up to recently focuses on either continuous or discrete random variables and is quite limited for hybrid Bayesian networks. So to give you an example, this comes from a study called LSAC, which is Australia's children's longitudinal study that look at different impacts on children's health, learning, social, and cognitive development. The 4 variables of interest that you're seeing here, the yellow one is MBI, which is the Z-score of the MBI of the child. SE is the Z-score of the social economics among all of the families. BM1 and BM2 are usually the BMI of the carers, usually the parents. The parent 1 is usually the mother, parent 2 is usually the father. So one possible graph structure that we can have from these 4 nodes is the first one, where you have BM1 and BM2, the children nodes of SE, and our parents nodes of BMI. So you can then write down the joint probability distribution of this graph as the conditional distributions that only depends on the corresponding parents in the graph. But this is not a unique structure. There are other structures that we can explore, and then can write down different probabilities accordingly. And for 4-node case, the number of possible structures can go up to over 500 structures. We predominantly focus on the Bayesian approach, in particular using MCMC for structured learning. The advantage of using this approach as opposed to other methods that focuses on greedy searches or other optimization methods is that it can provide a collection of samples from the posterior distribution of the graph given the data. That means inference can be made in the spirit of Bayesian model averaging. The possibility of conducting Bayesian model averaging is really important in high-dimensional domains with sparse data, where we usually cannot identify a single best structure from the data. And that means conducting inferences using the best scoring model is usually unjustified. So in a Bayesian approach, the score for a DAG is defined as its posterior probability given a data, which is derived from Bayes' theorem as follows, where we usually place a uniform prior distribution over the graphical structures. The marginal likelihood can then be obtained by integrating out the likelihood function with respect to the parameter prior over the parameter space. One MCMC variant that we are studying is partition MCMC, which makes use of the underlying combinatorial structures of DAGs in order to define new groupings and improve convergence when compared with traditional MCMC methods. To give you an overview of how it works, here is an example DAG that consists of 5 nodes, 1 to 5. A cyclic characteristic of a DAG means that it has to admit at least one node without any incoming edges. And we call these out points. So in this graph, you can identify node 1, 3, 5 as out points. And the idea is that we can reduce the size of a graph by removing these out points and their outgoing edges from the graph. So in this particular case, if you remove node 1, 3, 5, you would end up with a smaller DAG that consists of only node 4 and 2. And if we repeat this process, you gather the outpoint at every stage into a set, into different numbers of sets, we would end up with a way to rebuild DAGs recursively and enumerated. And it means that we can sample the DAGs uniformly. So in order to ensure that we account for every possible edge combination, for each of the node, the score of the permissible parents are summed, and then the score for each of the nodes is then multiplied, and the total obtained score will correspond to the posterior probability of a given label partition lambda. And then an NCMC scheme can then be built on top of the joint space of the partition and permutation. So at every step, we would then propose a new label partition, and this new label partition will be then accepted with probability alpha as defined here, where at every step we would calculate the number of neighborhood size depending on the move that we chose. Part of the previous work that we did was to look at the treatment of mixture of continuous and discrete random variables in learning the structure of Bayesian networks. In particular, we look at the appropriateness of a strategy to model all random variables as Gaussian, both from a theoretical standpoint via the expectation of log posterior ratio between the graph structures under different conditions and conducting relevant experiment and comparison. In particular, we use the BGE score for categorical data and the BGE score for continuous data. To give you an example of application of this, so this is the same the data set that was used before, the longitudinal study of Australian children when being put in a bigger network. So here the nodes are color-coded. So the red node is the target child's BMI. The orange nodes are the child-related variable. The blue nodes are the parents or the carers related variables, and the whitish nodes are the family or external factors. The edges, the red edges correspond to negative relationship, and the blue ones are positive relationships. So these are the top 2 most probable structures that you can learn from a small section of the data from a baby cohort that's under 3 years old. And from these structures, you can then make really insightful comments about the relationship of the variables. For example, the target node BMI, if you notice, is on the periphery of the networks and is only connected to the main network via only 3 nodes, which are the parents, carers BMI, and the birth weight of the child. The factor that is identified as the central node for both of these structures are SE, which is the social economic factors among all families. And this particular factor also adversely affects many factors. For example, the carer's BMI, the parent's BMI, the child's sleep quality, the family's diet. For example, FV here is the servings of fruits and vegetables per day. HF here is the servings of high-fat products per day. SHD here is the servings of high sugary drinks per day. It also indirectly affects the child's BMI as well as the family's mental health as well. For example, it indirectly affects DB1 here, which is a depression score for one of the parents. So to sum up, I just want to talk about some of the current works that we're doing. So we want to extend on the current work of the BG score, which assumes a normal wizard prior on the parameter. And because of the Gaussian's weight assumptions, is usually not very useful in domains with the underlying DAG structure is sparse, because the sample from the posterior distribution that assume Gaussian weights usually leads to high or moderate weights and more false positive. So we are working on building frameworks for different choice of priors, including Laplace, G prior, and horseshoe priors. We're also working to improve the current DAG sampling procedure, as well as tailoring the application for applications like gene regulatory networks or environmental and ecological systems that suited with the DARE themes. Thank you for listening.